know who's doing what. Every week, it seems Richard's producing lovely stuff. And we're all saying, oh, isn't that lovely? And I wrote an abstract the other week. Did anyone get that? No.
Yeah, I got that, and I thought it was good, Eugenie, and I thought it would go as an abstract to your article in that structure we already developed early on.
Yeah, well, I pulled up that structure and looked at it, and I wanted to make a few tiny modifications to the, like, you know, I don't think we should be talking renin-angiotensin system. I think we should be talking angiotensins. And then we get away with the kidney, circulating renin, blood pressure, and that's it. We've got to talk about angiotensins being generated in tissues by a whole host of things. And that's the critical component of thinking about angiotensin 2 and ACE2 and virus infection. So I wanted to do that. And I also wanted to have a schematic of what is the renin-angiotensin system and what are its functions before I went on to its dysfunction. As we've got it written in the document, we're starting with dysfunction, and I don't think you can do that without discussing its functions or the functions of angiotensins.
Yeah.
And we should be talking more than angiotensin 2, because angiotensin 3 and angiotensin 4 both use the AT1 receptor. And even I found angiotensin 1 to 7 does, but only moderately. Yeah.
I think that I've seen you've got that already in there, haven't you, Eugenie?
I put the abstract in. Yeah. Yes, I put that in. That was what I was, but it's not in what we have written as a. Oh,
I see. Okay.
As a session number 2. And so that I would like to sort of start on that, but I don't feel as though I know where to start. I mean, Richard's taken us to a point where we've got to get into the renin-angiotensin system. That's the next thing on, isn't it, Richard?
Yeah, it certainly is. In other words, it's now the dysregulation in the lung is the next step.
Yeah, but we've got to do the physiology and what the system does. You even can talk about dysregulation.
Yeah, I agree entirely. I think what I've learned in this whole process is, in a way, the whole COVID story has undersold the entire physiological role of angiotensin and its impairment in this disease. It's as if the virus is doing something totally different, whereas it's almost a RAS epidemic.
I agree completely. I think that's a lovely way of putting it. When you link it through to the TH1s and TH2s and Tregs, about which I know nothing, but you can certainly show effects of ACE inhibitors on those. You can bring in the whole immune response and your IL-6s and your IL-10s and whatever. And that has never been appreciated by anyone who thinks renin-angiotensin.
And in talking of the normal state, Eugenie, the key role, in a way, of that whole system is this fine balance, isn't it? This whole counterbalance between processes, turning one thing on, turning another thing off. And as such, that logically takes you to being a perfect target for disruption.
No, I quite agree. In fact, there must be a mechanical device, isn't there? What do you call that thing in mechanics where you have a controller?
There is.
Or it's not a feedback mechanism, it's an actual system that controls. So, you know, we're talking system.
It's a CISO thing, isn't it? System and system.
What?
Servo? I think it might have been a CISO, isn't it? Where you've got.
Yeah, there's servo processors, which Gary, in engineering, aren't there servo processors that do that automatically?
That's something I've heard of, but not really investigated. So I'd imagine so. I'd have to take a look. Yeah.
And really the reason it happens is to give biological processes in the human a degree of automaticity. In other words, if we had to think about everything in every system, we'd go crazy. And so we've devolved this process to push-pull servo systems that operate in a set of limits. I put a note out a minute ago. This disruption occurs with infections in many ways. The infective agents understand this. And cholera is classic. Cholera just turns on cyclic AMP and it's the switch, so it can never be turned off. And you just pump water out of cells into the luminal gut forever. And now for the virus, or for cholera, this is ideal because you induce diarrhea, and therefore you provide the setting for spreading. And likewise in the with this virus, in terms of shedding and using aerosols for spreading, is the same deal.
I was just going to say, I'm just looking at your emails. I've been out all day, but Bevan's reply about
The
cough, and there was a report in the paper today about a singer being able to project viral particles 14 meters.
Oh, good heavens!
This came from a case where there were a church in New South Wales where one side of the church got COVID and the other side didn't, and the asymptomatic carrier was singing to that side, and he did it for 4 days, 3 times a day or something. Anyway, the thing that we have not talked about is the fact that the tongue and the oropharynx are loaded with ACE2. And so every time I speak out, not just the nose, it's and Trump had it right. He wanted everyone to drink bleach.
Yeah, though it's not just in the mouth.
Trump wanted to inject it.
Yeah, he didn't want to gargle it.
Also, I think that would only deal with the mouth issue. It wouldn't deal with the fact of, I don't think it would still stop the stuff ending up in the lower respiratory tract, will it?
I don't know, but I mean, equally, I don't know that a nasal spray will stop at the oropharynx.
No. So,
you
have never worked that out.
But you had an iodine compound, Bevan, wasn't that right?
Yes, it's a well-known antiseptic, povidone iodine, betadine, and there are some. I can send around papers showing how effective it is in vitro in killing viruses.
Oh, I love it. I use it all the time for wounds and things like that. It was great on horses, but of course,
I think it's 1% is what you gargle.
Yeah, I'd be a bit worried about my thyroid after a while.
Well, if people have a thyroid problem, that is an issue, but if they don't, then there's no problem. The other option is there's a chlorhexidine mouth guard that would do if those people have an iodine thyroid problem.
Or eat oysters, Bevan. They're full of iodine.
So,
take amiodarone, but that's a tablet. That's buckets of iodine.
But still, this problem, I mean, even if you sterilize the mouth, it's not going to change the problem, is it?
Oh, no.
So I could never understand that line of reasoning. And Richard's work, I think, shows that even more. And you're right, Richard, in your email that you just sent that I missed about, you definitely do want to stop it going down to the lower respiratory tract. And the role of bradykinin probably is key in some of that as well. Yeah. Anyway, we're detracting from your need to get this sort of wrapped up, Eugenie. I mean, should we just, because I think Gary suggested that Richard should go through his slides, and I think it's great. And then maybe we should just focus on the structure that we've already got, that we've already discussed, to talk about how we're going to manage that.
Yeah.
Can I, maybe I could share my screen and just remind us of where we were with that.
Yeah.
So first of all, there was this.
Yeah, that's all I've got.
Yeah. So we have these ideas. Yeah. So we could revisit that again, but there was 6 main parts to this. So we had the background, how do we get here, problems with this approach, variability in individual biology and the complex physiology, a better way of thinking of this, and perspectives. And then what we then did is we then broadened that in terms of 9 papers. Yeah, so an overall theme, and forgive me, but I've just started putting some names in here in terms of lead authors, but the idea is that everyone would be contributing, or particular people would be contributing. So there's the overall theme, and I think really our letter to the editor is a good start for that. That would be my suggestion. Yeah. Then there's how did we get here, and I thought maybe Felix could take a stab at leading that. Thinking and acting differently. I think that ties in with the system science stuff that I'm doing, so maybe I could make a start on that. Then we've got data, information, misinformation, knowledge, and wisdom, and maybe this is something that Kerry could do, because I know she's still keen to participate. There's the host response to COVID and potential drug targets to prevent severe infection. So I don't know, but maybe that would tie in with perhaps long COVID, and maybe Bevan could do that. I don't know.
Yep.
Yeah.
Yeah.
Okay, so I'll add you to that one. Sorry, Bevan, if I've spelt your name wrong. I'll sort it out later. Antiviral technologies. Then there's the whole systems approach, perspective modeling. And I think that maybe this would tie in with what you've been doing, Richard.
Yep. Yep.
Digital healthcare technologies, we might not do that. We'll see. I had in mind someone who could work on that, but he's not been well, not COVID, but I'll talk to him about that. And then there's societal change and practice. Those were the different papers. Now,
can I ask, where is the biology?
Yes.
And the physiology and the pharmacology?
Yes. You can ask. Well, what's the answer?
Well,
it's missing. Are you saying it's missing?
It's seriously missing. And if we're going to underpin the whole story with angiotensins and what they do, somehow we've got to have that. I mean, paper 4 looks as though it should have it, but I don't know if Kerry.
Well, let's change it then. Let's change the tape. Change the title.
I wonder if you don't bring
more the host response.
The host response is the other one.
Yeah.
Yes. In fact, it'd go better in the host response.
Yeah.
But it's not just long COVID.
Yeah.
In fact, you know, long COVID is probably a continuum of COVID.
Well, how about we just retitle that to long COVID? Yeah.
I would have kept that one and had long COVID.
Oh, okay.
No. I keep host responses to COVID and potential targets to prevent infection. And I really think that that's Richard and I.
Yeah, I
Don't
think
you-
you can put the biology in there too.
That's what I'm, yeah, well, the
Oh,
biology,
yeah.
I would
'Cause-
do it like your, to a certain extent, like your paper.
Yeah, because I think regardless of what our genetics people tell us, you do actually have to understand the biology before you start thinking about drug targets. So I
Yeah.
think it all does fit. And because the long COVID is also physiology and biology, but it's they're different processes there than the initial kind of real fireworks that are going on when the disease is in the lung.
Yeah. I would put long COVID, yeah.
I was going to put Bevan next to that one.
Yes. Yeah. Sorry, I'm getting confused.
Right. Oh, yeah.
Yeah, I'm happy.
I think he's
I'm happy with
YN. Sorry.
You know, the other thing that you had there that I quite liked, although it was the chapter on data information and misinformation, because it is really, really hard to find your way through the literature at the moment. And there's so much crap.
Okay. We'll get to this one.
So I would keep that in as a.
Gary, I think it needs another one of your elephant cartoons.
Yeah.
But this one is where a whole army of people roll up with different pieces of an elephant. And the trick is how do you put it all together?
right.
Because that's what we're dealing with, isn't it, really?
Yeah.
And Eugenie's right. I mean, every parrot in the pet shop is pushing another picture out on COVID. So I think what we have to do is do something totally different. We have to in a completely different space and looking at this with different eyes, totally. And that's why, and some of it will be quite unorthodox. For example, if I looked at data and said, what did we miss out on in 2020? We missed out on good observational data leading to treating the host. And all the information is there. I mean, all the hospital records are there and so on and so forth.
Maybe that was combined with that.
But we didn't have the power or whatever to at our fingertips to, in a very, very fast way, to say, of the 2,500 approved drugs, these are the ones with patients are on where their survival was the best. That's what you should do.
Nobody's done that, have they?
No. And that would have given so much information early on in terms of treating the host. And you know, I'm quite astonished because we've got the algorithms, the facilities, and the ability to cross-link data and all the rest of it, but somehow or other, it didn't come to play. Part of that is there seems to be a devaluation that's gone on for about 20 years around the value of observational data, which I think is a bit sad, because observational data can be as powerful as randomized control data in the right setting. And so there's there are some real issues here that we need to address.
Okay.
Should you, I mean, all of this is very high tech, as it were. Should you, under say society changes and practice, incorporate the absolute historic value of quarantine and isolation and mask wearing? I've just been reading a journal called Lamfort's Quarterly. I don't know if anyone knows it, but it is a beautiful quarterly journal. And this one was on epidemic. And it goes back through all the epidemics in history. And today, as well, there was a paper from Taiwan pointing out that if you have contact tracing, etc., that takes your R from 2 down to 1.5, your R naught. And if you have masks and isolation, that drops it from 2 to 1.3. If you combine the two, you get down to an R naught of 0.83, which of course is, and that's been worked out from a study from Taiwan. So that virtually says that the society's practice in handling this virus, the answer's already there in the literature. I think that was in JAMA. I saw it today.
But Eugenie, this is where the biology and the power of viral mutation comes into play.
Yeah.
Because if you look at MERS and SARS, there's virtually no period where they are asymptomatic.
Yes, yes.
The real problem with this virus is there's a significant period where everything's asymptomatic, but the shedding's high.
Yeah.
And that's where the value of tracing becomes really, really important, because there's nothing else there. There's no assays, nothing. So all you've got is to be able to trace people and watch them.
But you've got to combine that, according to the Taiwanese, with mask wearing, because you mightn't have the right asymptomatic individual to track.
Yep, exactly right. And that's why that's where the tracing is absolutely essential, because the people who are traced are the ones that should be quarantined.
Yeah. Yeah.
The super spreader paper.
And the power of this, the power of this virus is exploiting that asymptomatic space.
Yeah.
So
the super spreader paper I sent round this morning from Nature makes out that the Japanese say backward tracing is more important, particularly when you've got a spreader, to identify, you know, where they picked it up from, rather than the forward tracing that is the conventional way.
Yeah.
I guess I sort of can understand that, Bevan, but because you've got to go back to the original spreader to make sure he's not spreading.
Yeah.
But
find out where he got off.
But equally, the person you've picked up, you have to go and get all its mates.
Yeah.
And isolate them too. But I was fascinated that the two together could really virtually eliminate the virus if the R naught value dropped down to less than 1.
Right.
And that's what the Taiwanese have done.
Okay, so where we are at the moment, we've got the overall theme. How do we get here with Felix? Knowledge, misinformation, thinking and acting differently. So I'll take that. Host response to COVID and potential drug targets. So that's with Eugenie. Long COVID with Bevan. Antiviral technologies we don't have covered yet. The whole systems perspective and modeling, Richard. Digital healthcare. I've got someone who might be able to do that. And then there's societal change, lessons and practice. So that's Kerry. Does that cover all of the subjects we wanted to cover? And if so, who could we approach to get to do the antiviral technologies?
That one is really interesting, because if I was to look at 2020, not much appeared in antiviral technologies, but I think that may change, because I noticed that Pfizer are just about to go into a phase 1 study with one of their antivirals, which tells me they must have some very strong preclinical evidence. And
the problem
yeah,
is that they're asymptomatic when they're doing, you know, the viral replication, and you don't know that.
Yeah.
I think the other thing, oh, sorry, Richard.
Go ahead, Jenny. Yeah.
No, I was interrupting. Oh, it's just that whole thing that you had on your slide. I can't remember which slide it was now, but there wasn't a good correlation between sort of antiviral load and infectivity, or your likelihood of going on to get disease. And so I know I've sort of been thinking about this more to dismiss it, that I think we need to have something in there, but we don't really want to give it any airtime, because in a way the global community lost a year of research focusing on hydroxychloroquine and antiviral therapies. And I'm not really sure that it's kind of like this bystander. Yes, lots of people get virus in their mouth and nose, but we don't really, I mean, it makes sense, doesn't it? I guess that if you stop the virus replicating in the mouth and reduce the expression and the number of, the number of virions, then you should reduce the likelihood of getting sick. But it doesn't seem to be correlated. It just means that you have less virus around. And in fact, the bigger issue is your ACE2 and your ACE system, or your angiotensin system. So I guess that, because the risk of that paper is that you get someone who's really either technologically good, or they're good with basic pharmacology and are looking at just standard antiviral stuff, which is what we do with HIV. But it kind of detracts us from the actual pathophysiology, particularly of the sick people in COVID. So I just say that because I think if we're going to do that, we should be really careful who we choose to do it. Thank you.
Yeah, it's an area. It's one that worries me, because the antiviral pharmacology is pretty complex depending on the nature of the viruses. And I mean, they do work with HIV is excellent, for example, but there you're talking about reverse transcriptase and basically incorporation in DNA, and totally different scene.
Yeah.
I'm wondering if when I'm looking at this, I'm saying to myself, from a standpoint of treating the host with existing therapeutics up and down the spectrum, how can we arrive in that at that position? And how can we arrive at that from data, for example? And the example that I gave of using observational data is one way of doing it. The issue of the host response to COVID is another way of saying this is how you can treat the host. The whole system's perspective will say, well, across this chain, where are the sensitivities and what could you be doing in terms of treating the host? Do you see what I'm saying?
I think the other thing you have to emphasize is the antiviral technology didn't work for influenza. The Tamiflu and the Valenza only shortened flu by about a day. And that's because the people didn't know they had the initial infection until they were showing symptoms. Yeah. And so I would think the same thing would happen with COVID.
Yeah.
But until you actually show some symptoms, it's a bit late to start with the antiviral drugs.
So it's a matter of thinking, isn't it? In other words, at the moment, people are thinking the virus is almost like a living creature and it's boring its way down this pathway. But it's not at all. It's an issue of if the virus never made its way to the lower lung, there'd be no problem. It would just spread.
Well, the example of that, of course, is HLN63, which gives responsible for 8% common cold, but in the old kid gets into the lungs and gives bronchiolitis and croup.
Yeah.
We all know that because we've all dealt with kids with croup.
Yeah. And there's something out there suggesting it may be involved in conjunctivitis.
Oh yeah,
which to me makes a lot of sense, because that's as infective as blazes. So So I guess if you re-looked at the whole thing and said, well, look, if this virus just behaved itself and stayed in the upper respiratory tract, there wouldn't be a pandemic. I mean, all you'd have is a virus like influenza making people feel a bit miserable and then spreading around the world. The real problem is the fact that it's dropping into the lower lung on a certain percentage of the population.
I wouldn't underestimate influenza. It kills a hell of a lot of people.
Yeah, it does. But well, of course, there are the different forms. There's the upper and lower, but the upper seasonal one, you're right. But it's nowhere near as severe in terms of the mortality as you're getting with COVID. No. The other thing that happens quite clearly is that the lethality of the viruses goes up dramatically in the lower lung, but the spread drops. And that's what you see with MERS and COVID. And, and so you don't hear this discussion going on at all.
That's really cool. Yeah, I like that.
Yeah.
Maybe one idea is that what we don't want in this is just a whole lot of knowledge and information being given to us for this, because I mean you could potentially write a whole paper on the renin-angiotensin system and a whole paper on antiviral therapy, which is interesting, but that's probably already done better somewhere else. So maybe if we were giving instructions to authors, it might be that we want to look at these other technologies and therapies that you think might be useful in a viral disease and explain why they weren't useful, or what the problem is with the thinking, rather than just list a whole lot of information. Yeah.
There was a great US commentator, I'm trying to think who it was Moran, who said that the obvious takes forever to see, the blindingly obvious takes an eternity. And I think that's what we're up against. We got the blinding obvious here and we're not seeing it.
Yeah. So I've taken it out for now. And we'll see if it's worth adding back in later. My thinking is that you know, with this new perspective, is there a place for this? And I think maybe we'll work that out as we go through. If this actually has any place or future in this scenario. Yeah, so if we just focus on these. Yeah. So in answer to your question, Eugenie, this one is yours.
Yeah, well, I mean, I would like to start thinking about it.
Yeah.
I feel frustrated and sort of not getting, I just want another question. We take what was in the original document, the first one you showed, and try and fit it into that paper. Okay.
Yeah.
I think then it might be a list of trying to make notes and build bits up and see where you know how it works out.
Yeah. And I mean, I don't know what your preferred way of working is, but maybe you could start putting together some slides on the topic.
I had done some. I sent them to you years ago.
Yeah, that's true. Yeah.
But I hate farting around with PowerPoint and things because I'm so clumsy. I would rather sort of sit down and
write.
Well, I'd like to sort of see what bits how it's going to be built up.
Yeah, yeah. Looking at it from a structural perspective.
Yeah.
Yeah.
Yeah. I mean, I couldn't produce anything as lovely as Richard's stuff. That's.
Oh, I don't know. I remember your presentation that you gave to your local group, which was very good.
Oh, the Royal Society. Yeah.
Yeah.
Yeah. Yeah.
Right. Okay, so that's that done. You feel better now?
Well, I feel we should be moving forward.
Yeah, yeah.
And I'm worried that, you know, we haven't got a concrete, we haven't got anything written down except the letter so far.
Yeah, but I think that was a really good start, defining that letter, because I think that sets the scene. I think that was important.
Yeah. But we've got to keep moving.
Yeah. And I've been doing work on system science and complexity, which and again I think some of that will have a part to play. So and you know, really that has been my main focus. So let's just hear about the letter first, Jennifer. Have you had any feedback?
No, and in fact, I actually had to write to them because I had a typo in your qualification. So I have actually been in email contact with them, but haven't heard. Maybe I should just double check that I received an acceptance letter, but I'm pretty sure I did.
Yeah, I had an email from them.
Okay,
I've had something from them. Yeah, so they must be processing it.
Well, they must be processing it. They haven't just knocked it back in 24 hours.
No, that's true. So, but they've been busy because it's, you know, Easter and COVID and everything, but
yeah.
Yeah, but they turn them around straight away virtually.
Okay.
Okay, so that sounds like it might be positive good. That we've not heard.
Yep.
Yeah.
Yeah, we're not dead yet.
Yeah. Right.
I speak from bitter experience.
Yeah, I think I had one turned around, rejected in 6 hours once from there. I think it was Lancet.
Yeah.
I was only just having a cup of tea to celebrate getting it off. It was already rejected. It's a bummer.
Yeah. Yeah, I've had a rejection from them as well on my original paper.
Oh.
Yeah.
I like your paper. It was really good to add that one in, I think, Gary, and the picture. When I saw the elephant, I just loved it.
Right.
I thought that's classic.
I might send you the link to the original paper I did as well on cancer inflammation and the 81 and 82 receptors, because there weren't many pictures in that one.
Oh, I read the Oshner Journal one, I think.
Yeah, there was one I wrote in 2004, which is about how cancer behaves in its local environment and stimulates the angiotensin system.
Yeah.
And becomes malignant as a result.
Yeah. But that's again another area where nobody quite likes the angiotensins being involved in cancer.
That's right. Yes.
We know that from bitter experience.
Yes. Yeah. Stay in your little box. Hypertension.
Yeah. Don't go near endometrial cancer.
Yeah.
Despite the fact the endometrium has a cycling renin-angiotensin system.
So, Richard, would you like? I mean, should we go through Richard's slides again? The new extensions to the story.
Yeah,
I made some comments on these.
Okay, and actually, the comments would be handy, and also I've put it together more as a reference source with the original papers where I've pulled the material from, so that we can then plunder it to put a manuscript together. I found it easier to do it that way.
I thought it was magnificent.
Yeah. So if we could start, maybe Gary, if you got them at that end, it's easier for you to do it than me.
Right. Yeah. Okay. Just hang on a second. I'll need to pull it up.
Have you got a cold, Gary, or are you being vaccinated?
I've not been vaccinated. No, I might have a little bit of a cold actually. I'll be surprised if I have, because I've not been anywhere. So I need to find my emails.
you're coming out of lockdown soon, aren't you? Is that right?
Yeah.
That's good.
Yeah. So it's our daughter's who lives in Reading is going to visit next week because the lockdown has been restricted.
Well, that's really good. I got my tickets in New Zealand, Eugenie.
Did you? You first asked them to go and buy one.
Yep, pretty much that day. As soon as I Jacinda Ardern announced it, we were on the web and got tickets.
Oh, lovely.
Like, we are out of here. It's so good in case they change their mind. Don't let us go.
Yeah, yeah. And I guess you don't care if you get caught.
Not really. I had to tell Brian Kelly that because he said, what about your teaching? I said, oh, I can do it by Zoom. He was trying to find a reason that it'd be good for me not to take the risk and go there and get stuck.
Yeah.
But, no, I just need to go.
Right. Google Slides. Okay. Right, I think I've got it.
Good. The what has struck me powerfully is that SARS-CoV-2 is really showing all the signs of viral tropism, and hence the title, the tropic mutant. Okay, next slide, Gary. To date, I'm convinced that the species jump is driven by the high affinity for ACE2 in the human compared to the vectors, be it bats or whatever. It doesn't really matter. Clearly now with the variants, that whole issue of jumping from human to human rather than species jump is now driven by the same process. In other words, SARS-CoV-2 has such a high affinity. It's for the ACE2 receptor. It's about when you look at most of the papers, it's around somewhere between 3, 4, 5 nanomolar. It's really right down there, and the variants are now down to about 0.5 nanomolar. So that's, in fact, you can see some of the experiments. The virus is not coming off the ACE2; it's binding that strongly. So anyway, it's the strength of that binding that gives the species jump. It's the strength of that binding that drives the virus to bystander cells from one cell to another. It's also the strength of that virus, which is now, that binding, which has now opened up the ability for the virus to go to the upper respiratory tract and to replicate and transmit from there at a very, very high rate. And of course, there's always the existing lower respiratory inflammation that you saw with not the precursors, but very similar viruses to that, like MERS and COVID. But if you stand back and look at it, and this is where I was coming to with the papers we're writing, if you strip everything away from the virus and say, well, look, don't think of it as a virus, think of it as a chemical, just like you would add any agent in a solution where it might be a peptide binding with a protein surface, for example, then the laws of mass action kick in, which are fundamentally logarithmic laws. And so that if you have replication and binding, then you'll process down that road of the law of mass action. So you'll go from the vector to an individual cell in a human, then totally within the human, then across humans and all the rest of it. So really what we're looking at in the pandemic is chemistry. You know, it's just the law of mass action occurring. The virus wants to occupy every ACE2 receptor site on the planet, and that's what's driving it. So the next slide.
Unlimited substrate.
Yeah, and so if you look at MERS, there were 2,000 cases up until 2020 because it's still rumbling on, and 866 deaths. In 8 months, SARS was the lid was put on it, and its total impact was nothing compared to what you saw within 5 months of SARS-CoV-2, where millions of people were infected very rapidly. And so the issue is to ask, what's that telling us? What's the difference between those viruses telling us? So let's move on to the next slide. In other words, what's unique around that virus as it enters the human? Next slide. And it's this, that the shedding in the upper respiratory tract is highly significant. And that's the and that's the key. And and I won't go into the details of all these, but I've just gone through paper after paper to extract this information. And you can see that if you were to summarize the whole thing, what you're seeing, in fact, is very significant shedding, heading towards, in some cases, the maximal shedding at the asymptomatic stage. Next slide. And this is the important ones, that the peak for SARS-CoV-2 is certainly in the first week in terms of viral shedding. But if you look at MERS, you'll see it's peaked at somewhere between 7 and 10 days. And COVID is out there as well. And so what SARS-CoV has managed to do is to push its peak earlier into the asymptomatic phase of the disease. And that's why it's deadly in terms of spread. Next slide. I'll just do something here. What these individuals here are highlighting, and that's Wolfram and the others, is that the high titers they're not only detected earlier, but the high titers are really explaining the spread so quickly and making it a virus that's so much different than SARS-CoV and MERS. And so it's a much more efficient spreading. Next slide. Now, this then takes us to where's that occurring? And if you look in that, in most of the evidence that's solid here, it's saying that most of this upper respiratory tract shedding and binding, obviously, the virus is on the cilia of the airway epithelial cells, and that's and that evidence is pretty strong. Next slide. And this slide I love. I mean, this is just an amazing piece of work. This is 2 data sets. On the left is one of them, and on the right is an entirely different one. And what they've done is looked at the expression of viruses along the bottom and that bind to different receptor targets that sit right on the axis there. So if you looked at the bottom on the left-hand side, you'd see ACE2, and you'd say, well, yes, SARS-CoV can bind to that, SARS-CoV-2 can bind to it, and so on and so forth. If you look on the extreme end of that particular plot, you'll see MERS-CoV binds to DPP4 as it does. And if you start with MERS, you see something interesting, and from MERS we can go to CoV. And that is that if you look at where the expression of DP4 is occurring, it's occurring around the alveolar type 2 cells, the same ones, in fact, that are attacked by SARS-CoV through a different binding site, in other words, ACE2. Very, very significant binding of MERS to the alveolar cells deep in the lung. But you can see hardly any binding at all in the nasal cavity at all, and not much to talk about in the lower airways. So it's all down in the alveolar area. So MERS-CoV, coronavirus, symptoms very similar in terms of lower respiratory tract to SARS-CoV-2, but binding not in the upper respiratory tract at all, but in the lower. its spread is minimal in humans, and you can see that from the data, and that fits. If you now go to SARS-CoV-2 binding to ACE, you can see the expression of the ACE2 in the nasal areas around the goblet cells very, very strongly. And you can see some expression down there on alveolar too, but intriguingly enough, much greater expression in the nasal area than down lower in the alveolar. It doesn't mean that the alveolar is insignificant at all. It just means that in the nasal area, there's significant expression of ACE2. However, or not however, if you then go to the second data set on the right-hand side, and a totally different data set, you see it's effectively the same thing, that the MERS is binding to the DPB4 deep in the lung, but not in the nasal area. The ACE2 has been expressed in the nasal area, but pretty weakly elsewhere. So what you would argue from all of this is that we know that SARS-CoV doesn't bind to the nasal area. We know that SARS-CoV-2 does. So SARS-CoV-2, through its mutations to its high affinity for ACE2, is now highly effectively binding to that relatively large capacity of binding sites in the nasal area. The other thing this tells us too, and I've seen this repeatedly, that the amount of ACE2 in the alveolar type 2 cells where the first attack does occur in the lower respiratory tract is very, very small. And so it's small, but incredibly significant. And so it's also worth keeping in mind that if you look at the anatomy of all of this, the nasal area, the surface area is very, very small compared to the surface area you've got with the alveolar ACE2 binding sites, which are not as big as a tennis court, but pretty huge. Okay, next slide.
Can I ask you a stupid question at this point, Richard?
Yep.
So, if people have low ACE2 expression in the nasal area, could this be one of the reasons? Could this be something which is, I don't know, a precondition for getting the infection in the lower lungs? You know, if you've got weak expression of ACE2 in the nasal area, does this mean that the virus has an easier path into the lungs, and particularly the lower airways?
Yeah, I think that's quite reasonable. I in a strange way, came around to thinking that that the ACE2 sitting on the end of the cilia were actually being protective.
Yes. Yeah.
And intriguingly, someone who's asymptomatic is asymptomatic because their ACE2 in the nasal area has looked after them.
Yeah.
But the price paid for that is they went and infected everyone.
Yes.
Yeah. It's kind of like it binds to the cell, the virus, and then it's taken up, and then you can't pass it down the tract.
Yes.
Yeah.
That's right.
Yeah. That's right. And in other words, you would have a degree of infectivity occurring, but the lid would be kept on it because of a robust immune system, for example. And you might have good T cells, and that's part of the reason why the young aren't fazed by that. They're actually being protected themselves, but from the standpoint of the virus doing what the virus wants to do, and that's to spread, then it's perfect. Because the degree of spread with MERS and SARS-CoV is minimal. It's highly inefficient for the virus. There's a lot of work, basically, if you're just going to go to the lower respiratory tract to get any spread. And where all you had to do is mutate, bind to that target a bit more strongly. You now got the tropism. You've now moved to the upper respiratory tract, and away you go.
Okay, good, thanks.
Next slide. And this is an important one as well. and it's a bit, sorry, it's a bit blurry, but again, it's an expression one. And what it's showing is where you've got the expression of ACE2 and TPMR 552. Now, you can see where you've got the precursor there in the nasal cavity. What it's showing is that the other component of entry into the cell, apart from the binding initially of the ACE2, which is the TMPR, is co-expressed alongside ACE2 in the nasal area quite strongly. And so I think that's important as well. And you can see also right down the bottom that there's plenty of it co-expressed in the alveolar type 2 cells as well. So it all kind of fits. So you could almost argue that if TMPR is expressed in cells, the rate limiting step is probably the ACE2. And the ACE2 is directing where this virus is going to go to. Okay, next slide. Okay, the question then to ask is, well, why is it replicating in the upper respiratory tract? Then, and this is a lovely piece of work by Wolfel again and others, and their hypothesis to say, look, there is tropism occurring in the throat, and they would argue that a logical way of arguing this through is to say that this is the difference between SARS-CoV and SARS-CoV-2 in terms of the sequences in the spike protein. And in other words, the S1, S2 junction is where there's the difference, and there's that furan cleavage site in there, which I view really as another way of saying, well, it's a difference around binding. So put up the next slide. And here, this is the work from Lan and the rest of them. It's very good work, where they've measured the KD, the binding coefficient of SARS-CoV-2 and SARS-CoV. And these groups, and it's now quite amazing, the figures are coming out very similar. It's around the 4.65 nanomole mark for SARS-CoV-2, which is incredibly high affinity for a binding site. And for SARS-CoV, it's about 30 odd nanomolar, and you see that difference occurring all the time. So you would argue the difference between those two affinities is the reason why you've got tropism and why it's binding up in the upper respiratory tract. In other words,
why does the furan cleavage site affect the KD?
I think it affects, and I might be wrong here, Eugenie, but that site is a hinge for the molecule. And when that's loosened or cleaved, it makes the bit that's binding to the ACE2, it presents it in a stronger way to the ACE2, right. is my reading of it. So we can go to the next slide. Now this was the paper where, it's a brilliant paper where what they did is they looked at the binding of ACE2 to the virus, and then they engineered the ACE2 synthetically in different ways to increase the binding. And their view was to make a therapeutic that would be a dummy that could be fired into the lung that would bind the virus, so the virus wouldn't go to Jenny and your model to the lower respiratory tract. It's very, very, very good work. There's no question about it. But what I'd like you to do is look at the extreme left-hand column, A, D, and G. And the top two are SARS-CoV-2, and under that is SARS-CoV. And you can see the binding figures there. I've got a binding figure of 3 for SARS-CoV-2 for the ACE2, and about 15 for the CoV. So you've got that 5-fold difference again coming out in them. By engineering, on the right-hand side of that, by engineering the virus, you can get down to incredibly low levels of binding, like 0.23 nanomolar, for example. The other thing that's of interest, if you go to the panel G, G is our NL63, which is the common cold virus that we were talking about before, the coronavirus that's responsible for croup and other things. And you can see there now that the binding coefficient's right out to 22 nanomolar. So I'd be arguing that really what the virus has been doing is it's been concentrating on improving its binding to the ACE2 receptor, and that's driven the tropism. And also, if you look at the new variants are now sub-nanomolar. They're binding down at about 0.5 nanomolar to the ACE2. And so there's, we'll get lower and lower KDs as we get more mutants in this process. And so we'll get to the point, which would be quite worrying, where it's no longer a KD. For example, if you look at SARS-CoV-2 binding on C, there's no value. And the reason there's no value is they couldn't get an off reaction. And so I assume what that meant is that the binding was so powerful it didn't come off. Okay, next slide. So if you look at now, if we move away from SARS-CoV-2, and this was picked up by an Italian group, Petrosilo, what they highlighted was the fact that tropism in virus binding in the respiratory system has been well established with influenza. In other words, seasonal influenza H1N1, that was, by the way, the 1918 pandemic one, and H3N2 bind to the upper respiratory tract, primarily through the linkages, Bevan, that you referred to a minute ago, where you've got the inhibition with Tamiflu and others occurring. And then in the lower respiratory tract, you have the avian influenza H5N1 binding, again to sialic acid moieties, but at the 2,3 linkage. And so what you've got is less severe cases occurring with a seasonal influenza, but greater transmission. And that's why we see it spreads throughout the world, and that's why we get vaccinated every year. Whereas with the avian influenza, the fatality rate is incredibly high. It causes very severe outcomes, but would be less because of the tropism is less transmittable than the H1N1, which is in the upper. So really what in COVID, what we're seeing is the SARS-CoV-2 is doing exactly what the influenza virus has been doing for years. And that's saying, if you go up to the upper respiratory tract, you can spread to the population much more efficiently. Next slide. And so what I'd argue is that the first step really is the binding of the nasopharyngeal area. And this kind of fits. In other words, there's this high transmission here. And the problem in getting this message across to anyone is that while there are a large number of deaths throughout the world, and as tragic as that is with COVID-19, it actually has a lower case fatality than does SARS-CoV and MERS-CoV. The reason that the number of deaths are so high is the infection rate's high because it's being carried through tropism through the upper respiratory tract, and with the greater binding, obviously, to the ACE2. Now, with a certain percentage of individuals, it will move from the upper to the lower and becomes severe COVID-19 disease. Now, in those individuals, it now takes on the same characteristics as SARS-CoV and MERS. Next slide. And so we'd argue the high affinity of SARS-CoV ACE2 enables the virus to bind a nasopharyngeal. ACE2 replicates, transmits efficiently from the upper respiratory tract. That is, the viral tropism is based on the ACE2 affinity. And then you get pre-symptomatic infection or mild illness. What I've said down the bottom is, paradoxically, this virus tropism can be viewed as a benefit for the asymptomatics. The nasopharyngeal ACE2 provides a barrier to sequester SARS-CoV-2, thus preventing potential dangerous exposure of SARS-CoV-2 to the lower respiratory tract. Next slide. Now, this Italian group put forward this model, which I quite like, and that is what they're saying is the start is upper airway colonization and escape from that upper airway within the human and not across humans, an immune escape. In other words, the immune system hasn't arrested it. And then you drop down into the alveolar epithelial type 2 cells, and now you've got the ACE2 infection occurring there. And then they run this down through 3 phases, which I quite like, because I think when my reading literature says it's pretty much this way. It's the SU dative phase that's occurring originally, and then it heads on to proliferation, then fibrosis, and so on and so forth. And so there's a lot of dysregulation now kicking in when you get down to that level, which is really the issue of the next set of slides that we'll work our way through. Okay, Gary, next one. Okay, when you're down the bottom there, you can go from moderate illness to severe to critical. Let's just move on, Gary. Yeah. And what's important is all that predisposition plays heavily into inflammation, and with all these comorbidities, they track into that inflammatory state that's now occurring heavily down in the lower respiratory tract. Next slide. So if I go back to where we are, we've got the jump from a vector to a cell, and where the vector has been infected, but takes many, many virus particles to infect it, because the ACE2 binding is poor in the vector. In the human, the binding's higher, fewer virus particles required to get in to replicate, and therefore fewer particles required to infect bystander cells, and away the whole process goes, so that the binding to the ACE2 is driving the spread. Next slide. If you take the cells away, you can replace them by humans. In other words, you can look at the binding as the driver throughout an individual, but you can look at the binding as the driver across the population in exactly the same way. The fact the ACE2 has a human hanging on it in a chemical sense is almost irrelevant. It's the binding that's key. Next slide. And so we'd argue the high affinity of SARS for the ACE2 gives you the nasopharyngeal entry by tropism. The viral titer is peaked at the first symptoms. The nasopharyngeal replication and rapid human-to-human infection and transmission before symptoms occur asymptomatically drives the spread, and hence the global spread. And traveling with that in the next slide is the fact that a certain percentage of those individuals infected will then go on to major inflammatory lower respiratory state. So that tells me the following. It tells me that RAS tropism is driving the global spread. In other words, the binding in the upper respiratory tract where transmission is maximal, and the serious disease is coming from a percentage of those individuals where the virus has made it into the lower respiratory tract, where you see dysregulation again of RAS driving the inflammation. So RAS is driving both of these components. Next slide. So what I've said is upper respiratory tropism to permit the highly efficient replication and transmission is dangerous, not because of the spread of upper respiratory infection, but because it brings with it life-threatening lower respiratory disease at scale, not seen with previous dangerous lower respiratory virus infections such as MERS and SARS. And I think this is the genesis of the pathophysiology of COVID-19. This is how it starts. It starts at this point where it's it's mutated to the point where it can now maximize tropism. Next slide. And so the yellow bits is where we are. What's left is to now look at the drivers occurring in lower respiratory inflammation and the dysregulation of RAS, and going beyond the lung then into the vasculature, endothelial cells, heart, and so on and so forth, which we should be able to do in the same in the same way. But it's in this diagram at the bottom, it keeps reminding me that from the perspective of the virus, it's achieved what it's wanted to, and that is to get maximum spread. And it's almost as if, from the virus's perspective, the chronic damage left behind is inconsequential to its spread. That what we're doing is mopping up. The pandemic is the mopping up of a fundamental law of mass action. So that's where we are.
Yeah.
So if you go back to that Italian, sorry, that's my dog killing another dog. If you go back to your Italian paper,
yep,
you can actually bring in angiotensin 2 in all those pathways.
Oh, you can.
I mean, angiotensin 2 activates NF-kappa B and stimulates.
Exactly.
You get this whole process here.
Yep.
You get fibrosis, and you know, it's possible even other components are important. So basically, all you've done is take away the ACE2 receptor and left this to sort of go on its own merry way. I guess back to what Gary, was it Gary who suggested that the more ACE2 receptors you have in your upper respiratory tract, the greater a protection you have. So why aren't we using nasal sprays and recombinant?
I think it would make a lot of sense. I once suggested, that the most effective mask you could make would be one that had ACE2 bound to it.
Oh yeah.
Yeah,
there's a good idea.
But Eugenia, let's pick up on your point here. It's what has puzzled me is that the amount of ACE2 in the alveolar cells is very small. But it's very important. And I think it's a trigger response. And I think two things happen. One is if you disrupt ACE2 and through autocoids and so on and so forth, you trigger the nearest mast cells to respond, then you'll get a degree of inflammation. It may not be that significant, it may be local. And in the normal course of things, in keeping the lung clean, this might be quite appropriate. But I think where it all goes to jelly, literally, is when you open up the gaps in the endothelial cells, and now you start to get intrusion of circulating elements, because now you're starting to bring in some serious kinins and some serious chimases and God knows what else.
Well, you're also bringing in angiotensin 1, which
you are,
and angiotensin 2. I mean, what was interesting to me, you've got the lung being continuously perfused by angiotensin 1.
Exactly.
Because that's the gateway to angiotensin 2 in the arterial circulation. And
exactly.
I was going to ask whether once you get this, do you also get the endothelial ACE2 infected? Because then it becomes very nasty.
Very.
And I think the ACE2 endothelial reaction is inflammatory, procoagulant, and every other nasty thing you can think of.
Yeah, I think when you get to this stage, it's almost out of control. And by that, I mean the following, that when we've just looked at angiotensin, but you raised earlier, and quite appropriately, and I've gone back and it's coming back into discussion more and more, the kinins and bradykinin. I mean, the bradykinin will drive that leakage of plasma agents right into the tissue. And the minute you do that, you're driving kininogens right next to the mast cells, and you've got DABK and bradykinin all over the place, and so you've got both arms of that system running.
And you're not looking at renin. You're looking at chimases and anything else that is a protease.
Yeah. So it tells me that by picking this apart, I might be a bit simple, but that early stage, if you remember the Lewis triple response with histamine and serotonin and so on and so forth, I mean, if you could block that first stage with something as simple as an antihistamine, you may not progress. I'm not saying an antihistamine will prevent COVID by any means, but if you understand the timing of this process, you may be able to arrest this by existing therapeutics. Do you follow what I'm saying? Yeah.
Mind you, by the time you detect a wheel and flare, you've had your response, haven't you?
That's the problem, and that's why the virus has got it. But of course, the other thing, of course, is the mast cell stabilization, and that's where Fedsin's coming from with the statins, because the statins are so good at that. And but why wouldn't you be looking at chromal sodium and things like this? Yeah. But anyway, so I think we've got a picture that says this is why it jumped. This is why it went through. And by the way, the picture also says that if young kids have been exposed to the NL63, their systems are all tweaked, ready to go to handle this, and that's what you're seeing. And when you're like me, your B cells can't remember anything, and so it's all over Red Rover.
Yeah, listen, I don't like the not having a decent immune system, I must admit.
Yeah.
I think it's only part of the story.
I
don't really, I mean, you talked about dysregulation with the influenza pandemic the other week. That was quite a neat story. And I can't help coming back to things like the high prevalence of autoimmune disease in women, and yet they're protected. And they are partly protected by COVID. And pregnancy is a condition where there is, a lot of inflammation going on because you're getting implanted by a foreign tissue. And I was hearing this morning how thyroid function changes in pregnant women. They get sicker than if they're not pregnant with thyroid disease. And that looks as though it's an activation of some autoimmune system. I don't know.
So let's tease that out a bit. With what I picked up really from the 1918 analysis that's been done, says that obviously with the Russian flu in 1890, that you had a perturbation at a time when your immune system is being formed. In other words, the first year or two of life. But it seemed to me that the worst combination was the following. It was a combination where you raise through your beta cells specific antibodies for the Russian flu, but very generalized T cells for influenza. So when the new one came along, your antibodies couldn't remove the H1N1 in 1918, but your T cells said there's a problem here and went straight into inflammation mode and stayed there. And so you've got again in the immune system a dysregulation that's not dissimilar to the dysregulation that we see with ACE2, where one component is gone, the very necessary component.
Well,
Because
extrapolating that analogy, would you suggest that all those older people who've had severe colds and coronavirus infections throughout their life are doing the same thing?
yes, exactly. In other words, if you've got T cells that are recognizing coronaviruses of the past, but you've got no antibodies to remove them, then you're going to drive an inflammation state, and you're not going to stop that inflammation state. So I think we can, it's the same thing all the way through. It's a dysregulation game. But I think we can map our way now through the lung, into the vasculature, out into the other tissues, and so on and so forth, going in the same path. Then I think we'll get as good a picture as anyone's got of of the life in this virus, from the time it left the vector to the time it's someone's recovered from it or died from it.
Is this another argument for immunizing the young rather than the old in terms of reducing the infection rate?
Yeah, well, I think ultimately, maybe I step back a bit. I think the issue of spread is gone. I mean, that horse is out of the stable. The issue really to me now is the mutations.
Yeah.
Now, a lot of people say that the mutations will come from areas where there's no vaccine. And that may be the case. In other words, but I can't, from an evolutionary perspective, think why the virus would want to do that. Because it's doing quite well if it's up against nothing and can just spread. I think it's more likely to mutate in areas where we've put up a barrier, i.e. a vaccine.
I don't know that you can make that discrimination.
No, it couldn't be that.
It's a random, they are random events. Interestingly, every one of them affects the receptor binding domain. Yeah. And I mean, you've got billions and billions of particles replicating. You're going to have billions and billions of mistakes, and some of those will be nasty mistakes.
Yeah, they will. I
agree. The virus can't think. It has no motivation. Anything that happens has got to be a mutation, random.
Yeah. And
I was just driven to, there was an amazing study done some years ago in a video, which showed bacterial resistance. And in other words, they had an agar plate with 3 sections in it and differing doses of antibiotics. And they started with bacteria, they loaded on one section, and you actually saw the bacteria sitting very actively in the agar plate. But then eventually it burst through. Now, the reason it burst through is one of those billions of combinations, Eugenie, that you were just talking about, was the mutation that let it get beyond the pressure of the antibiotic. And then it got to the next chamber, and then it did the same thing, and then it jumped into the next chamber. So that when you push on these things with
I don't think you have to push. That's where I disagree.
Oh, I see what you're saying. Yeah.
Isn't the Kent variant in UK responsible for about 98% of the infections?
Yeah, it is. And that would have occurred before the vaccine. Yeah.
Yeah. I just think, I mean, it's a barrier. I agree with you. Yeah. And it doesn't matter whether you've got, well, I suppose if you've got the disease absolutely rip-roaring throughout a community, the chance of mutation is going to be higher.
It is. Yeah, it is. And there's no thinking logic to the virus. Well, it's a chemical entity at the end of the day. But anyway, that's that's where we are.
I'm running off, guys, because it's 5:30. I gotta go somewhere else. Sorry.
Yeah, I ought to go
but
to work as well.
Yeah, you go to work, and I'm just gonna work on my structure,
Yeah.
my bit.
Yeah, well, I'm going to do the
so that
same.
we can.
That sounds like a good idea.
And we see you in a fortnight.
Yeah.
Yeah.
And thank you, Richard, for all of that.
So I'll push on a bit into the next bit, but feel free to modify and change it. I mean, these are just ideas and concepts coming up. So, we'll get into the next bit, which is the lung, and then on to the vasculature, and then on to other tissues, and then and then we can see where we are.
I must say, Richard, I don't know why you don't think you've virtually got a paper there.
Well, I think if we get all the way through, we probably have. Yeah.
I mean, you've got to a point where the thesis is, this is why it's got a high, this is why it's infectious. This is, look at this against COV2, COV and MERS, and it's a beautifully clear-cut story.
Yeah.
I don't know that I'd be putting more. I would put a next chapter would be or pathology or whatever.
Jenny can tell you I'm terrible at writing. I just kind of move on to the next bit. So
I think you're good with writing. I'm just a slowpoke because it takes me ages to read what you've written and understand it.
So Jenny, we might talk about drafting it out and then circulate it to everyone. We'll see how we go. Yeah.
Right.
Okay.
I think it's a very convincing story with a lot of data, and it actually makes a whole lot of refreshing points to me. So I would like to see it published.
Oh, well, yeah, I'm more than happy to do that. But I've got to make myself do it. And, you know what I mean?
Yeah, well, some of us know exactly how you feel.
So, yeah, because I've got a student who he's got a couple of papers that I'm in the middle of at the moment. I've got to get those done as well.
Yeah, it's too much to do.
Yeah, but we'll get there. But it's challenging, and I like with this group the different way of thinking of things. That's really just it's this horizontal way of and not vertical obsession.
Yeah. No, I appreciate that too. And we all see it from different perspectives as well, which are all complementary.
Yeah. Oh, there's no question about it. So we have to do another elephant type cartoon, I think, Gary.
Okay. Never heard of elephants. All right. I'll see you in a couple of weeks. Yeah, but if we could all do some work thinking about our structures for the papers, that would be great for next time.
Yep, I think we've got to move on.
All right. See you soon.
Bye.
We are moving on.
Nothing like getting a kick out the pants. Okay.
How about your
Right. Bye.
Bye.
Bye.